Okay, the last item in here is related to this. Let me create in here a tab again for item 4, and actually type item 4 and the rest, I think, or 6 or whatever that number is. Anyway, so basically, in this case, so those are some of the consequences that we have based on this observations by Mr. Kepler, the theory of Mr. Newton. So I have an understanding now of the motion of the planets. These are all the 8 planets that we know of: Mercury, Venus, Earth, Mars. Skip Ceres for a moment. That's a dwarf planet, part of the asteroid belt, actually. And then you have Jupiter, Saturn, Uranus, and Neptune. Here you have their semi-major axis. Remember A? And also you have their period, how long it takes for them to go once around the sun, and their eccentricity. In here, what you need to pay attention to the following. All of these numbers, they're in astronomical units. So, for example, 1 AU, that's about 150 million kilometers. Okay, some 90 million miles away from in miles. Okay, I try to stick with the SI, so please don't have to remember the non-SI units. So 150 million kilometers, to be specific, it's 150 billion meters if I'm going to be talking in terms of meters. Okay, so that's one thing. The other thing also is that the period is measured in years. How long in terms of our own years? For example, Mercury does almost a quarter year around the sun. So that's one thing. The eccentricity is how close is it from a circle, or how far away is it from the circle. The higher the number, the further away from the circular path it is. So Mercury is a very, very eccentric path because it's a very big number. Venus and Earth, they're eccentric but not that much, okay? So they're almost circular paths. Mars is an eccentric planet. That's one key element in here. Ceres, which is not actually a planet but a dwarf planet that belongs to the asteroid belt, that's actually also has an eccentricity which is kind of high a little bit. So just to see that this is 0.09, and it's almost 10 times bigger than that of the Earth. So the path of, for example, Mars would be something like this versus the path of the Earth, which is almost circular path. So that's something to give you an idea about the eccentricity. Neptune is circular, Uranus, Saturn, Jupiter, they're less circular, and that's basically what that eccentricity is. Now here are the planets. They're in black color in here in this picture. Basically their paths. As you can see clearly, they're almost all of them, they look like circles. But they're not quite right circles because they're slightly off circles. So the sun is not exactly in the sun, but it's a little bit off of the center. So even the sun wobbles a little bit in the motion when it's influenced by the rest of the planets. So it's not exactly going around its center of the symmetry. It's going slightly off of the center of the symmetry because of the influence of all of these things. So the center, the sun itself is actually moving away. So if the planet moving this way, the sun moves in the opposite direction with respect to their center of mass. We'll talk about that down the road. Anyway, that's one thing. What is in blue in here are all asteroids. So these are asteroids, parts of the asteroid belt, and this is Ceres that I was talking about. This is the biggest one of them and the one that is well known, and you probably should remember that. And then in the red ones in here, they're all actually comets. And one of the famous comets, as I talked about also, is Halley's Comet. That's one of the things that was predicted using Newton's laws. So these are some of the things that basically we can use the mechanics that we learned from Newton to explain Kepler's laws. Finally, one of the things that actually also we use down on Earth is the spacecraft and satellites. Satellites are extremely important. Without them, no GPS system, no TV reception, for the most part, no communications can be established on Earth. So they're extremely important for our daily basically experience, including our communications and so on and so forth in here on Earth. So I just want to bring more real estate in here just to see stuff that is hidden. Anyway, uh, one of the things is when we launch an object on Earth, I can throw a rock right now. It's going to follow a parabolic path, and fall. But if I throw it fast enough, it's going to try to fall, but it's going to stay in orbit. So there is in here a velocity with which an object can escape the pull of the Earth, and that object will live forever. So this is called the escape velocity of an object. So object can stay in orbit, that's what we want, or object can be basically expelled from the Earth completely, at least so that they reach infinity with a zero velocity. That's what that expression means. So in this case, an object that is given that velocity will escape the Earth completely. For the Earth, we know that the escape velocity is 11.2 kilometers per second. That's a big speed. So if you're imagining a spacecraft trying to reach, for example, Mars or something else, it needs that speed to leave the pole of the Earth. So that is basically, every planet has its own escape velocity. If you saw the movie Mars, The Martian, for example, Mars itself has an escape velocity. When Matt Damon was trying to measure the velocity, he had, of course, different velocities in there, and actually the escape velocity on Mars was a lot less, so that's why he didn't need that much, basically, fuel to leave the planet. So those are some of the applications that we have for all of these things. Another thing in here is that, wait a minute, the objects in the solar system, for example, if I take the sun, and let me go back in here. If I have the sun, for example, and I have a planet that I'm studying, let's say Mercury, for example, I'm trying to explain its path. Well, Mercury is not just subject to the sun. There is Venus, which is not too far from here. When Mercury and Venus are in here, there is a distance between them. So both, yes, it's attracted to the sun by a big force because the mass has a big mass, but it's also attracted to Venus when it's on this side. Now, if they're in opposition, namely that if I have Mercury this way and Venus is on the other side, then in this case, Mercury is being pulled toward the sun by the sun, and it's also pulled toward the sun by Venus, although it's going to be a very, very small force because of two reasons. Venus itself is a lot smaller than the sun. Number two, it's in this position, it's going to be further away. So the two work against it, so the effect will be a lot less. So there is less force on one side and more force on the other side. But that's not the end of it. There is actually Earth in here too. And that's not the end of it. There is actually Mars. There is actually Jupiter. There are all kinds of objects in here that influence. So the problem can be very complicated if you try to think about it that way. And you really have to come up with some sort of solution to it. And usually, the biggest object, the closer object, has more effect than the further away object, the smaller object. So that's basically, in a nutshell, what's going on. So this is what happened then. Uranus was discovered, okay, by Herschel in 1781. It was actually discovered accidentally. So we saw Uranus there. Here is a planet, and people started studying that planet. Okay, that's the seventh planet in the solar system that we didn't know exists. If we knew about it, we probably would have more days in the week than 7 days. We'll have 8 days, another day for Uranus. So at that point, Uranus was discovered, but there was a problem with its motion around the sun. The measurements were off by this much, 0.03 degrees from the actual calculations. So the observation and the calculations did not match. So two people independently, John Adams on one side, and actually John Leverrier from France, one of them is English, the other one is French, in 1845 and 1846 independently, to account for that discrepancy, to account for this small, minute perturbation in the path of Uranus, they hypothesized that there is a planet out there, and that planet, they measured its mass, they measured its location, they were off with 1 degree in space, that go and look for it. It must be somewhere specifically in the solar system. Here is the region where you need to look for it. Of course, when the telescopes were directed there, that's how Neptune was discovered. You see the power of math in here in this case, and how science come together. We discovered Uranus, and then we use the math to predict the position of another planet, Neptune. This is actually the driving force also behind Planet 9. We suspect that there is another Planet 9 out there, just by looking at the path of the so-called TNOs, the trans-Neptunian objects, basically Haumea and Makemake and all of these dwarf planets past Pluto, Pluto, Eris, and all of these objects in there. We're looking at their path and we see something is funny going on with their paths. So that's why Planet 9 was hypothesized, and people are working very hard day in, day out, either to reject that hypothesis or find actually Planet 9. So that's basically what's going on right now. So this is in a nutshell chapter, basically the one dealing with the gravity. So I'm gonna stop the recording in here, and hopefully you guys gonna finish the homework. If you guys have any question, I know I went very brief in here, trying to keep these recordings under 15 minutes. I'll try to keep them under 10 minutes if I can, under 15 minutes. But I know I'm very fast, going very basically briefly on it. I urge you that you read the book. Number two, if you have any questions, please do ask it. There is a discussion board. Please go and create discussion item in there, or ask me and I will create the item for you. And then we will have a discussion in there and I will answer your question in there. And hopefully we will finish this stuff in here and do the homework and do the quiz and other things that are due this week. Thank you.